Okay, so in this discussion I'm going to go over pressure and airflow in a building. So as you can see here, we're going to discuss the relationship between pressure and airflow, look into the basic physics of what causes air to move, and then discuss the difference between a thermal boundary, an air or pressure boundary, and then what can cause pressure differences inside of a building. So when we want to maximize the efficiency of a building, maximize the safety, maximize the comfort, we need to have a couple of things, specifically with regards to air and heat flow. Okay, so first of all, we need a fully insulated thermal envelope. So the thermal envelope is basically the insulation. So thermal meaning heat, right? So the think of the envelope, right? So the thing that encloses the building. The thermal envelope prevents heat from escaping the building. That's different than the air boundary or the pressure boundary, which is the same thing as the air boundary, which needs to be tightly sealed. So the air boundary prevents air from moving. The thermal boundary, the thermal envelope, prevents heat from moving. Very important but subtle difference. They can be the same, but it depends. They're not always the same. Those two layers, the thermal and the air boundaries, they have to be, to maximize your efficiency anyway, they should be in completely covering the building and in contact the whole time, right? So you should always have, whether it's a wall or ceiling or a floor underneath you that has unconditioned space on the other side, you should have insulation the whole way across, and you should have a nice tight air seal as well. Also, the equipment has to be well sized, which we'll talk about that in a little bit. Also, you want to have a well balanced air distribution system if you have forced air, and healthy indoor air quality. So let's talk about a few of these things. So thermal boundary just limits heat flow between inside and outside of the building. So it's in the image here. Whenever you see this sort of squiggly thing in a wall, in case you don't know, it's the sort of universal symbol for insulation. Okay, and so the insulation is your thermal boundary. Remember, the insulation prevents heat flow, not necessarily airflow. Sometimes it does both. But you need, again, you can see in this image that in orange is your thermal boundary, and you want to have it continuous all the way around the building, all the way around the building envelope. Okay, it's really important. We'll do this calculation later, but believe it or not, if you're, let's say you have like a ceiling above you, right? You look above you in your ceiling, and it's really well insulated, but you're missing 7% of that area. That can actually drop the total R value of your whole ceiling by 50%. And we'll do that calculation later, but that actually is, it's not a one-to-one relationship. So it's not like you're missing 5% of your insulation, it's 5% R drop. It's actually about 40 to 45% R drop. So it's really important to be continuous all the way around. And so, if you're in a house, like this is a residential building, it could be a small commercial building, I suppose, thermal boundary is really easy to pick up on, right? You can see the insulation here. It's not great because you can see it's not even, and you can see some of the framing members here down on the floor joist, and that's a sign that there's probably not quite enough insulation there. But anyway, the point is thermal boundary is usually pretty easy to pick up on. Now the air boundary, or the air barrier on the other hand, that prevents airflow from between inside and outside the building, right? So it's represented here in the red color. And you can see, again, ideally you want to have air boundary continuous all the way around the building, or all the way around the thermal envelope, or excuse me, building envelope, sorry. And it should be in contact with that thermal boundary as well, right? So insulation should be have an air boundary all around it as well. So the thermal boundary is usually pretty easy to pick up on. It's the insulation. The air boundary, or the air barrier on the other hand, isn't always easy to pick up on. So there's some tools that you can use as a energy auditor, which we may have time to get into, maybe we won't. But if you are interested, we can go over a blower door and how that works. But it's not always easy to pick up on. Okay, so if you're going to manage the airflow in a building, it's in and out of a building, it's really important you understand what causes air to move. It's actually really simple. Air movement requires a hole. Okay, so you need to have a hole, a way for the air to move, and then you need a pressure difference across that hole. That's it, actually. So pressure is what causes air to move. If you're in meteorology, that's what causes the wind to blow, pressure differences across the globe, and the wind is actually that pressure sort of trying to balance out. So areas of high pressure, the air flows from the high pressure areas to the lower pressure areas, and that's just what makes air move. And so the magnitude of that airflow changes based on the size of the hole. So a bigger hole or a bigger pathway, all else being equal, you're going to have more airflow, and also a bigger pressure difference, or delta P, and you will have more airflow. Okay, so that's really important to remember, that those two characteristics: bigger hole, more flow; bigger delta P. You want to jot that term, delta P. Remember, that's the triangle delta P, or difference in pressure. The greater that is, the more air is going to flow as well. And another really important property of air in and out of a building is that we in the U.S. we measure it in CFM, or cubic feet per minute. So you want to jot that down. Airflow takes the path of least resistance. Excuse me. So like if you have air moving in and out of a house, if you open up a window, it's going to move out. You know, and then you have like little leaks in the attic or whatever, attic space. It's going to move out. That the air is going to flow through the open window before it goes to the attic, because it's less resistance. It's a big open hole. Another really important thing to understand: anytime 1 cubic foot per minute leaves a building, another cubic foot per minute has to come in somewhere else in the building, and vice versa. If you force a cubic foot of air into a building, that means a cubic foot of air is leaving somewhere, and it doesn't always come in and go out of areas that you want it to, and you can't necessarily control it. You can have some measure of control if you have like ventilation, and you can have air intakes, you can have forced ventilation, forced exhaust, but it's really important to remember: CFM in equals CFM out, and CFM out equals CFM in. So you have an exhaust fan in your bathroom on the 3rd floor, exhausting 50 cubic feet per minute out the building. That means 50 cubic feet per minute of air are coming in somewhere. So it could be coming in all the different places. It could be coming in through the basement. It could be coming through the attic. It just depends. But it has to come back in. And the air, again, moves from high to low pressure areas. And the air usually moves from high to low temperature areas. It's not always the case. We measure pressure in the U.S. in pascals. You want to jot that down, a pascal, or abbreviated capital P, lowercase a. If you want to know what that means, think of like one post-it note. You put it on your hand. That weight, that's about 1 pascal. Okay. And if you're in the HVAC field, you'll probably use inches of water column, but we'll use pascals mostly in this class. There's a couple different kinds of leakage. Okay, so you have direct leakage, which is when the air goes in and out the same spot. You can see that on the image over here. Think of an open window, right? Air's coming in, air's going out. Indirect leakage, these are the sneaky leaks where it's kind of like a one-way path, right? So this image here shows some air coming up through a soffit and then leaking in through a wall. It's only coming in one direction. So that's usually a little bit harder to pick up on. And those are the tricky ones that you can use tools like a blower door to pick up on. So obviously the direct leakage is going to be easier to spot. There's also a difference between infiltration, which is air that leaks in, exfiltration, which is air that leaks out, and then ventilation is when you control the leakage, right? So like a bathroom fan, a kitchen fan, those are ventilation. On HVAC, which we'll talk about later, we need to provide enough fresh air for people in the building. And so that's ventilation as well, because you're purposefully bringing in air. But you do want to jot down these 3 terms: infiltration, exfiltration, and ventilation. And there are a number of things that force air leakage. We'll talk about each of these in a little more detail here in a minute. So again, to reiterate, pressure is what causes air to flow. So in order for air to flow, you need to have a pressure difference between 2 areas, and you need to have a way for the air to move between the 2, right? So you need a delta P and a hole, basically. The bigger the delta P, the more that air is going to flow. The bigger the hole, the more that air is going to flow, right? So delta P is this difference in pressure. WRT is something we use a lot in the energy auditing field, so you want to jot that down. It's with respect to. And the important thing to remember is that if you have a delta P, that means you have a difference in pressure, which means you have to be referring to two different areas, right? So like inside of a building, outside of a building, on the second floor, up in the attic, whatever the case may be, there's always the delta. It by definition means you're measuring the pressure between in two places. And so the with respect to, it's important to know where you're measuring the pressure. So am I measuring the pressure in the basement with respect to the first floor, or the basement with respect to the outside, whatever. So that's what with respect to means. Okay, and so again, if you have on the left we have a building that's pressurized, okay, so it's high pressure with respect to the outside. And on the right we have a building that's low pressure with respect to the outside. So I want you to think about which way the air is going to flow if we have these little gaps in the wall. So again, high goes to lower pressure, high goes to lower pressure. So it inside outside, you know, to like physics, it doesn't matter, you know. Air is just flowing from higher pressure areas to lower pressure areas. Could be from inside of a building to outside of a building, could be from a basement to an attic, attic to a basement, doesn't matter. It's going to flow from the high pressure to the lower pressure areas. That's just how it is. That's how a fan works. That's how a pump works. I mean, all of that just works by changing the pressure. And so again, it flows from the higher to lower. Remember, every CFM that enters, a CFM leaves, and vice versa. And flow always takes the path of least resistance. Okay. Okay, so that's the introduction to pressure and airflow. So now you know what causes air to move, what's the relationship between pressure and airflow, the difference between a thermal and air or a pressure boundary, and then what can cause pressure differences within a building.